Hi, folks. Today we're going to talk about the Mandelbrot set. This is a biggie. And so, what is the Mandelbrot set? Well, the Mandelbrot set was one of the first computer-generated fractals, and it changed our approach to using technology to solve problems in mathematics. Remember how we used the four-color theorem and we proved that using computers? Well, this is something which we could only really explore using computers. And so we knew that iterating complex functions led to interesting geometries, but could not fully understand their behavior. The Mandelbrot set gave us a way to classify these geometric objects and demonstrate just how infinitely complex these fractals could be. Before we talk about that, though, let's talk about functions on complex numbers. Now, we all know what complex numbers are. They're numbers which have an imaginary component. And so we can write them in the form a plus bi, where a and b are real numbers, and I is the square root of -1. That's an Algebra 1 topic. What we might not be as familiar with is how we can play with them when we're dealing with functions. One way we often visualize them is using a Cartesian coordinate system, similar to this. And so when visualizing a number z equals a plus bi, we often think of a Cartesian coordinate system and say a, the real part, will correspond to the x direction, and the b will correspond to the imaginary part in the y direction. And so in this case, the point 2, 1 would correspond to the complex number 2 plus I. And we could do this for any number. If we wanted to, we could go over here and we could say this value is going to be -3 plus 2i. We can get values in all four quadrants. Now, the behavior of complex numbers is very similar to the behavior of real numbers, with one big exception, and that is whenever we have a power of I, we can simplify it. And so if we have I to the first or I to the fifth or I to the -3rd, that's just I. If we have I squared or I to the sixth or I to the -2nd, that's just -1. I cubed, I to the seventh, I to the -1, we get -I. And I to the fourth is I to the eighth is I to the 0 is just 1. Every 4 powers of I, we return back to 1. And this cyclical nature is what links it to trigonometric functions. It turns out that e to the a plus bi is equal to e to the a times cosine of b plus I sine of b. And so this tells us e to the pi I is equal to -1, and e to the 2 pi I is equal to 1. That is some very weird behavior, and you'll never guess who came up with it. It was our good friend Euler. Euler seemed to do a lot of math. When multiplying imaginary numbers, you have to remember to FOIL or use the appropriate distributive formula. And so, for instance, if we have 2 plus 3i times 1 minus 4i, we can just FOIL it out. And when we FOIL it, we will end up with 14 minus 5i. If we have 2 plus I squared, well, we can square it just like we would normally, and we'll end up with 3 plus 4i. If we are multiplying conjugates, and so 3 plus 2i times 3 minus 2i, it turns out we end up getting real numbers out of that, which is where the Gaussian integers can become kind of interesting. The idea that 13 is a prime number in the reals, but when you're dealing with Gaussian integers, you can rewrite it as 3 plus 2i times 3 minus 2i. It leads to questions of what is a prime number in the Gaussian integers. So when we're talking about functions on complex numbers, well, a function on a set of complex numbers works the same as a function on real numbers. You have inputs and you have outputs. If you have f of z is equal to z squared minus 1, well, this would take an imaginary input, square them, and then subtract by 1. If you want, you can also break up functions in terms of the real and imaginary parts, but usually we just keep it as something like this, where we're just treating it as functions of z. And so one of the challenges is, how do we visualize something like this? we're taking something which we've decided we're going to visualize in 2 dimensions. And so that's what a complex number is, a 2-dimensional point. And then in order to show how it's changing, we would need 4 dimensions, because to go from 2 dimensions to another 2-dimensional space, you need 4 dimensions. Can't really do that, not easily. And so one way we often show the behavior is to map the image of a collection of points. And let's try that. And so let's use this as our sample function. F of z equals z squared minus 1. If we begin at the point 2 plus I, and so here's our starting point, 2 plus I in red, then when we evaluate it, we end up getting 2 plus 4i, which would be this point up here in blue. And so looking at the graph to the right, we have plotted the starting point in red and the image in blue. What happens if you do more points? Well, here's 25 points and their image. And so consider the function f of z equals z squared minus 1, just as in the prior example. To the right, if we take 25 different points and we map them out, if we plug all of those points into this function, this is the graph we get. This is the output values. We can see how it's taking this square and it's kind of stretching it in different ways, almost like it's rotating away from some point. That's generally what we'll see when we start dealing with stuff like squaring complex values. Well, this idea of squaring complex values was something Julia was very interested in. And so to begin with, let's talk about what it means to iterate a function. And so to iterate means to repeatedly apply a function. For real valued functions, it's not that hard. And so let's consider the function x squared minus 1. If we plug in 0.5, we get negative 0.75. If we plug in negative 0.75, we get negative 0.4375. If we plug that in, we get negative 0.808. We could plug that in and then plug the next thing in and just keep plugging it in over and over and over again. That's what it means to iterate a function. And so in this case, what happens in the long run? Here's the first couple values, the first couple iterations. Well, in this case, we end up getting values which seem to get closer to the values at negative 1, 0 and closer to 0, negative 1. My guess is what's happening is we're going to end up oscillating close to these two values, but we're probably going to always be in quadrant 3. In this case, we could say that upon iterating it, the values are going to remain bounded, meaning they are not going to explode out to infinity. If we started at a different value, it might explode out to infinity. In fact, if we start at 1.7, it gets really big really fast. And so if you plug 1.7 in, and then you take the answer and you plug that in, and you plug that in, and you keep going, after 6 iterations, this function will give you 867,000 as an output. Clearly, this is different behavior than starting at 0.5. And so starting at 0.5, everything remained bounded. Starting at 1.7, everything remained unbounded. Where might be the point where it stopped being bounded? Well, Julia was interested in this, but he was interested in complex functions. And so functions of complex numbers. And he did the same function just with complex numbers. And so mathematician Gaston Julia in the 1920s was curious about this question for complex numbers. Given a complex function, what values will remain bounded upon iteration? To simplify things, he mostly focused on this one function, z squared minus c, or z squared plus z, or plus c, for various values of c. Note, this predated computers, so it was tricky to study. And so if you're starting with z squared plus or minus c, what could happen? Well, what Julia discovered is that for the function f of z equals z squared plus c, depending on the value of c, the bounded region looked radically different. We call these sets Julia sets. And to the right, this is what it would look like for C equals -1. You can see this would be the real axis, and then this would be the imaginary axis. And so this is still the complex values. While the term fractal didn't exist yet, he recognized that there was some form of self-repeating pattern. And without computers, it was very difficult to fully understand or represent these sets. And so if we think of z squared plus c, and we are picking values for c, and we're trying to figure, for some particular c, and so we choose -1 for c. This is the set of values which are going to remain bounded. If we iterate 0, 0, and we keep plugging in 0, and then we get a value out, and then we plug that value in, and then we keep plugging it in, all of the stuff in black is going to remain bounded. Everything in a different color is telling us how quickly it's going to escape out to infinity. And so that previous one was what happens when c is 1. Well, here's what happens when c is equal to 0.276 plus 0.536i. Here it is for c equals 0.25. Here it is for 0.32 minus 0.5i. Notice for these first two, it's connected. For this one, it's completely disconnected. And so the question is, why? Well, I didn't have a good answer. And so while the shapes took many forms, they all had some form of self-repeating pattern. It also seemed that there were two types of sets. If the value of 0 remained bounded, then the set was completely connected. If the value of 0 became unbounded, then the set was completely disconnected with values similar to the Cantor set. And so at the time, there was no good way to determine which values gave Cantor dust, like the graph to the right, or which gave connected regions. And so what was causing this? And what would the map look like? If we wanted to figure out all of the C values which make it so that it's connected, or all of the C values which make it unconnected, well, what would that look like? How do we figure it out? That's where the Mandelbrot set comes in. And so this came at the dawn of computers. And so the Mandelbrot set is the set of C values for which the function f of z equals z squared plus c will have a connected Julia set. A function f of z equals z squared plus c was found to be connected if iterating the function starting at z equals 0 remained bounded. And so really just checking that one value and seeing, does it stay bounded or does it blow up real quick? It was first developed in the late 1970s, though as computer technology improved in the 1980s, we got increasingly better renderings on it. And so this is one of the earlier images, but let's see the next image, which is a much more detailed version. And there we go. And so you can start to see how complicated this thing's looking. We have all of these different lobes, and in every single one of these lobes, it's describing a different characteristic of the Julia sets. If we choose values from anywhere on here, it's going to describe some different Julia set, whether it's in this black area where it's going to be connected, or even out in the blue area where it's disconnected. You can also see different colors around the border. That's showing the number of steps it takes for something to escape off to some particular value. And so how long does it take for something to explode off to infinity or leave the unit circle or something like that? When trying to classify Julia sets, we can think of the Mandelbrot set as having different lobes. These lobes are different contained bits of the Mandelbrot set. So each lobe has Julia sets which are generally similar to one another. And so if we were to pick something from up in this top lobe, all of the Julia sets are going to look fairly similar. If we're choosing from a different region, like let's say this region 3, they're all going to look kind of like this. If we're choosing from something in this central lobe, they're all going to look kind of like this. If we're choosing something over here, we're going to get something like this. And so we end up getting that all of these different things or all of the different regions are going to give us some different shape. Everything outside of the Mandelbrot set gives you Julius sets shaped like disconnected Cantor dust in some abstract design. And we start to see that a little bit. I don't know if we've got any graphs of it here, but we can go back up and see the example here where this is Cantor dust. This is basically isomorphic to the Cantor set. It's completely disconnected, and you can actually structure it in the same way as the Cantor set. When we zoom in on the Mandelbrot set, we get more Mandelbrot sets. And so the Mandelbrot set describes a set of fractals, but it is also a fractal itself. And so to the right is a zoom on the boundary of the Mandelbrot set, where we can see another little Mandelbrot set. The different colors, again, signify how long it takes to get outside of a certain bounded region. And some versions of the Mandelbrot set can get very colorful. But you can see just how intricate this is. As we zoom in more and more, we're going to get more and more complex structures. Oops, there we go. And there's infinite complexity to it. And so as you zoom into the Mandelbrot set, you begin to see just how complex this thing is. This is a zoom of the image 62 million times in one region. And so what's so enticing about this is that it came from just a simple equation. This is a quadratic equation. This is a graph of a quadratic equation. We're talking about x squared minus c for some various c. And if we just repeatedly apply it, we get something as complex as this, something that looks almost alive. And that's where we start to realize that when we have some function and we iterate it, we can get infinitely complex things. This one is one of my favorites, the multibro set. Sometimes we opt to explore other functions using this same technique. And so if we iterate a function of the form f of z equals z to the n plus c and do the same type of analysis, we call it a multibro set. My favorite is this one, which is a portion of the multibro set with an exponent of 6. And so z to the 6th plus c. Iterating most any function can have similar analysis done to it, and the fractals will often be just as complex and interesting. And so why do we care? That's always a very good question. An important question to always ask is what is why do we care? Good, I'm good at reading. In the case of the Mandelbrot set, you're not going to use it to fix a washing machine or improve your tax bracket. It's not going to happen. One of the main applications of the Mandelbrot set is using it as a tool to test new technology. And so consider the first Mandelbrot set created in 1978 to the right. This is the first one, and they were able to create it using a series of asterisks. Think about how far we've come in the technology. And much like the Cantor set can be used to test objects in analysis, we sometimes will pull a Mandelbrot set just to really put math to the test. More than anything else, though, it really speaks to existence. It speaks to the idea of life and infinite complexity. When we think about how long the world has been around, it's seen a lot of waves. It's seen a lot of fluctuations. It's seen a lot of iterations. And in seeing all of these iterations, we end up seeing all of the biodiversity, which is all around us. All of the complexity of the world is very easily explained by simple equations. I mean, the Mandelbrot set was x squared minus a number or x squared plus a number. That's very simple. And the forces which we are experiencing from gravity and things like that are all just simple structures too. And so when we think of chaos theory and fractals, perhaps the most important takeaway is the philosophy of chaos. From such simple initial conditions, we can create such great and complex structures. The Mandelbrot set is a beautiful example of this. If you take x squared and iterate it enough, you get something that looks almost alive. What is fascinating is that our entire world is formed from such structures. All life, all mountains, all planets, and all natural structures are just a consequence of iterative processes. Consider a wave hitting the shore. How many waves have hit how many shores in the last 4.5 billion years? That's a lot of opportunities for chaotic behavior to create amazing things. And we are all examples of that amazing thing. With that, I'll let you get to work exploring where you find the Mandelbrot set in the real world. Good luck, folks.